So now, while reviewing all this stuff, we've gone through what an object is and how they hold state and how they have behavior, and we've seen different types of objects. But we also have to talk about this specific type of object, this type of class in Python called an immutable class. An immutable class. Now, right, immutable, mutate, mutator. We're going to get to that term later on, but it means to change. So immutable classes cannot change. You are more familiar with these than you might think. Boolean, integer, float, string, tuple, frozen set. These are Python's immutable classes. They are unable to change once established. Now, I know that you think that that sounds crazy. Let me pull up the interpreter window. Let me grab a new one. Pull this over and we go, okay, x equals 5, and we can say, I think it's type of x, and we get it's an int. X equals 6, and we'll do type again, and it's still an int. We've changed it. We can see that. But what you think is happening isn't actually happening here. So, let's use our old trick. Let's look at the underlying memory address. Print hex ID X, right? So here we go. Here's the ID of hex. I'm sorry, the ID of X, which has 6 inside. And now let's change it back to 5. Do the same thing. You notice that the memory address changed. And look at this difference. Not only did it change, but 5D, 9999 AA, 870F00. It changed by 16 bits, right? This, the 16s digit, what we would consider the tens digit, but remember, hexadecimal. The 16 digit reduced by 1, and the 2 to the 16 digit reduced by 1 as well, right? So I guess reduced by 1 is not the right way to put it. This jumped all the way back up to the top, this reduced by 1. Just like if we had 900 and 890 and we were comparing, right? It's the equivalent concept here. If we want to see what's happening, let's take this and not make it X and make it 5. 6. Remember, our memory addresses right now are being stored inside of a variable. That's what's changing. What's changing is not the data, it's the reference to the data. So you can see 5, this is the memory address for 5. Python, when it starts up, and you're going to hear me say this a lot, Python does not give one crap about your computer's memory allocation. It is a memory hog. So it goes through and it pre-declares many low integers and slams them into a list. So we just jump up to the next slot in the list, right? And you can see this right here. So what's changing when we give a variable a new value is that we change the reference at X to represent the data that's at a new position. How is this different from mutable classes? I mean, we can do this again. Let's change X to a list of 2 elements, right? And we can print out the hex, and then we can change it to a list of a different 2 elements, and we can print out the hex, and we can see that that hex changed. So clearly, things can't be that different, right? How are they different from mutable classes? Well, here, of course, this is going to change the memory address. Remember, this is the literal form of the list. We are saying, hey, create me a new list with this data in it and assign that to X. So of course it's a different memory address. That's what we're asking the computer to do. But let list, set, and dictionary, right, are data structures that have mutator methods. And we can see now that X has changed. But now our memory address hasn't. Look at this. That's the same memory address. This is the difference in mutators versus immutable versus immutable classes. You can alter the data at reference. Oh, I guess I did 1.2 and 3.4, whatever. You can alter the data that is being referenced without having to assign a whole new memory address, right? So then I guess the next question is, how do we tell if 2 variables are the same? And a lot of you out there are going, okay, now the professor's had a stroke. I get that. But double equals, which is something that a lot of students at this level will forget. If it makes you feel any better, I forget it sometimes. Every now and then, I write code where I say, hey, if X equals Y, right? And that's not the proper code. It's double equals, right? This is what checks for equality. But there's another operator that Python has available. Is. So we get double equals and is. What's the difference between these two? Well, we come back to our list. Okay. Now remember what we talked about. We created a list. X equals 1, 2, 3. And then we say Y equals X. So what happens when we run this line of code? Well, we say, hey, I want a variable, right, called Y. So the interpreter takes a variable and creates a bucket called Y, and it takes whatever's in X, which is the memory address, to this list, and it says, copy that memory address into Y. So these are called aliases of each other, which means that they point to the same memory address, right? X append 4, so now we get 1, 2, 3, 4. What happens when we call the same for Y? What do we get in Y? Well, we get 1, 2, 3, 4. Because remember, Y points to the same memory address as X. So when we do this, we're going out to that memory address and altering what's there, right? They are just 2 different buckets pointing to the same list in memory. So if we say X double equals Y, X is Y. Well, that doesn't do us any good, does it? Okay. Well, what about this? What if we say X, what if we redeclare Y? And we say Y equals this. Y is an empty string. And we'll say for element in X. So for each element in X, Y dot append element. Right? Now we go X, now we go Y. Why is this different? They're still the same. Well, remember what's happening when we do this, right? This is the literal. This is the literal constructor. So we're saying, hey, create a new list for Y and append the data, append the elements. So if we go print hex ID X, and we do the same for Y, we're going to see, take 2, that they're pointing to, now I grant you, this one is interesting because these are very close in memory. Normally you don't get ones that are quite this close in memory, but these are pointing to different blocks of memory. Wow, that's crazy. They really are super close. You don't usually see them this close. That's what? 256 times 3 memory addresses away, right? 16 squared, yeah. So what's that? 768 bytes apart? That's weird. But they are different memory addresses. So equality says, hey, let's check and see, do they contain the same values? And we're going to see what equality actually means later on. But for a list, what it says is, are they the same length? And if they're the same length, is the thing at index 0 the same, and then the thing at index 1 the same, and then the thing at index 2 the same, right? And for is, this operator means not are the values the same? Do the two lists contain equivalent things? It says, are they literally pointing to the same memory address? So this is the difference between these two. And that explains why a lot of the times you'll see this check. Because in early Python 3, none, which once again you'll see has a memory address that represents none, which seems inside out, right? None is the representation of nothing. Why should nothing have a memory address? That's Python's solution. Remember, in Python, everything's an object. So in early Python, the logic was none doesn't really have a value. None is the absence of value. So double equals, that doesn't really make any sense. How can I check the equality of something and nothing, or nothing and nothing? So that would have caused an error. Nowadays, you can do this. And if you put this in your code, I'm not even going to correct it, right? But this is the more logical way. And when we see what this is, how this is implemented behind the scenes, how this is actually a covert method call, this will make more sense, especially if X is none. Because how do you call a method on none? Right? Something to think about.